All right, well, okay, here we go. This is 5.1b notes, 5.1b notes, simplifying trig expressions using identities. You are more than welcome to read through this. Basically, what we're going to do today is we're going to take complicated trig expressions and use identities to simplify those. And the question is always for simplification, how far do you go? Like, how far do you simplify? And I think what I want to try to say is you want to have the least possible trig functions in there, and I want to talk about in a second what that means. And you don't want to have any fractions in there. So if we can make that happen, that would be awesome. So these are a few methods. These are the methods that I'm going to use, okay? So the first thing you want to check for is squares. Can you use any Pythagorean identities, okay? If you can use any Pythagorean identities, replace those first. Then you're going to group or factor, then switch to sine and cosine, and then we can start reducing, okay? A lot of times we have to like factor out common factors or combine fractions, find the least common denominator, things like that, okay? So this is day one, so we're going to try and make this, trying to ease into this. So if you look at sine theta times cotan theta, okay? There's no squares in here, can't really factor anything, but what I can do is I can rewrite cotangent theta in terms of sine and cosine. So I have sine theta, let me zoom in here for a second. I have sine theta times, well, cotan is cosine theta over sine theta, right? We used a quotient identity here. And then this should be, well, sine theta times 1 over sine theta. These sine thetas cancel out, and what we're left with is cosine theta. And that's our final answer. So we use the quotient identity to simplify this. Next up, again, check for squares. I don't see any squares, so what I'm going to do is I want to express all of this in terms of sine and cosine because doesn't seem very obvious if I can factor anything here, and it doesn't really seem like I can. So I have cosine theta times sine theta times, well, tan theta is sine theta over cosine theta. Cosecant theta is the reciprocal of sine, okay? And that should give me, all right, well, sine theta and sine theta, they cancel to 1. Cosine theta and cosine theta cancel to 1. So we have sine theta times 1, which is just sine theta. Now, and again, no fraction, and try to use the least amount of functions you can. Next up, cotan theta is cosine theta over sine theta. Cosecant theta is 1 over sine theta. Keep, change, flip, or multiply with the reciprocal. That means that sine theta times 1 is sine theta. And cosine theta and sine theta multiply here. Cosine theta. So the sine thetas cancel out. We're left with 1 over cosine theta. Now, again, we're trying to not use fractions here, so this could be expressed as secant theta. Okay. Alrighty. Let's see. Let's see what else we can do here. Secant theta over cosecant theta. That should be tan theta. Let's see if that's correct. 1 over cosine theta over 1 over sine theta. Multiply a fraction. To multiply a fraction, we multiply with its reciprocal. So basically, this is 1 over cosine theta. times sine theta over 1. That is nothing else than, I should really work vertically here. Let's go ahead and get in the habit of working vertically for these. Sine theta over cosine theta, which is tan theta. Good. Reciprocal identity, secant theta is 1 over cosine theta, cosecant theta is 1 over sine theta, and at that point it's just algebra. Okay. Next up, okay, we have squares. So squares is always our #1 priority. I know that sine squared theta plus cosine squared theta is 1. So this whole thing literally simplifies to 1. And then this is 1 over cosecant squared theta. Well, the reciprocal identity tells me here that 1 over cosecant squared theta is nothing else than 1 over sine squared theta, which is nothing else than sine squared theta. So Pythagorean identity or reciprocal identity, if you go straight from here to there, I'm pretty happy with that too. That should be fine. Okay, let's go ahead and finish up page 1 strong. Secant x minus cosine x. Okay, looks like there's something going on here, but in order to figure out what's going on, I'm going to rewrite secant theta using the reciprocal identity as 1 over cosine. When I say theta, I mean x, because the argument just changed, minus cosine x. Okay. Now, if I want to subtract two fractions, I need to make these a common denominator. And how I'm going to make them a common denominator is I'm going to expand this fraction here by cosine x. Okay. Think about this like 1 over 3 minus 1. Let's just say that. Well, this denominator is 1. In order to make these common denominators, you need to expand this fraction with 3. So that's 1 minus 3 over 3 over, you got negative 2 over 3. So this is the same spiel, but now we're just using trig functions in order to make that happen. So what I'm going to have going here is one long fraction bar, cosine x in the denominator. This one didn't change, so this is 1 minus, well, cosine x times cosine x is cosine squared x. Okay, now we're going to work with something. 1 minus cosine squared x. Okay, if you think about this identity, sine squared x plus cosine squared x equals 1, you can solve that for 1 minus cosine squared x. So this should say sine squared x equals 1 minus cosine squared x. So 1 minus cosine squared x is nothing else than sine squared x. So you're going to replace the numerator here with sine squared x over cosine x. Okay? In a perfect world, this would be like completely, like, the question is, what is simplification, right? Sometimes it's easier to have it in terms of secant x minus cosine x, and sometimes it's easier to have it in terms of this. Now, what I would really like you to do in order to get rid of fractions, we can write this as sine x over cosine x times sine x, and that is nothing else than tan x sine x. Okay? Again, what's the purpose of the simplification? We just need to always make sure that we have purpose with what we're doing. All right. Let's go ahead and finish this. 1 minus sine squared theta. If you take this identity right here and solve that for 1 minus sine squared theta, that should be cosine squared theta. So we have our first Pythagorean identity in the numerator. And then I know that cotan squared x plus 1 equals cosecant squared x, right? So what I can do here is I can say cotan squared x is equal to cosecant squared x minus 1. Subtract 1 from both sides. So this is cosine squared x over cotan squared x. or theta in this case. What's important here is that we keep track of that this is actually an identity, okay? Furthermore, I know that cotangent squared is cosine squared over sine squared, and over sine squared theta. And this should, you know, multiply with its reciprocal. We have cosine squared theta times sine squared theta over cosine squared theta. And then I know that these two bad boys cancel out, so we have sine squared theta as the final answer. It is super crucial, okay? Crucial right here to write the argument, okay? Because what we're going to do sooner than later is we're going to change the argument, and then there's going to be a whole lot of trouble going on, okay? So I'm going to show you an example of wrong work. This is wrong work. Do not write this as, well, this is cosine squared over cotangent squared, you know, and then I just keep simplifying. This is cosine squared over sine squared. No. All right, this is a whole bunch of rubbish. This function, in order to evaluate anything, needs an argument, and that argument is usually theta for us. So do not forget the argument. The argument will prevail. Hope you guys enjoyed the video. We're probably going to let you guys practice on these in class, and which is something that you should do right now, and you can go ahead and check the key to see if you got it right or wrong. Enjoy. This is my favorite unit. Yeehaw.